घर पे कुछ पढ़ते हो? कैमरा ऑन करो ना सभी। So we have about how many 20 students हैं। तुम ये कर लेना, अटेंडेंस का देख लेना तुम। हाँ, किसी जगह जब इसमें भी हो ही रहा है इस टाइम रिकॉर्ड, कितने प्रेजेंट थे। ओके चलो मैं स्क्रीन शेयर करता हूँ, हम शुरू करते हैं काम। तो अभी हम हान बनाख थ्योरम कर रहे हैं, बेसिकली उसी की कॉन्सिक्वेंसेस एक तरह से। एक मिनट जरा मैं इनको एंटर करता हूँ, एक दो और आ गए। So we have 22 students. Okay. So let's start. उसी के कंटिन्यूएशन में हम करेंगे आज व्हाट्स कॉल्ड अ बानाख लिमिट। कोई नहीं, फान बानाख थ्योरम की एक तरह से कॉन्सिक्वेंस है ये भी, but it's regarding a particular space, that is space of bounded sequences, जिसको हम कहते हैं L infinity. So you already know what's L infinity. L sub infinity, small l infinity, is equal to all sequences x equal to x1. चलो मैं एक कलर बदल देता हूँ, मुझे कल लगा था ये कलर अच्छा था। x1, x2, so on and so forth, such that xi's are scalars and there exists some, let's call C positive, such that xi is less than equal to C for all I greater than equal to 1. So bounded sequences of, और इस पे जो norm है, तो in case you remember, it is actually suppose norm of x, जहाँ हम छोटी सी infinity रख दे हैं, is equal to supremum over I greater than equal to 1 modulus xi. And since it's a bounded sequence, so it is bounded as a set. And if I take its moduli, then that's a bounded set of real numbers. And a bounded set of real numbers has a supremum. So this is how we define the norm that you already know. Then it has a subspace C. C is all convergent sequences. Yani it is sequences of the type x1, so on and so forth. इसी तरह से xi are scalars and limit exists. Yani ये they converge, these sequences. I approaches infinity exists. तो कहने का मतलब ये sequences converge करती है, and you know that every convergent sequence जो है, that is bounded. So C is a subspace, a proper subspace of L infinity. और मैं चाहूँगा तुम इसको भी revise करो। मैंने उस time कहा था C sub 0. All convergent sequences to 0 is a subspace of C, and which is a proper, and the C00. All sequences that vanish after a certain stage, they also converge to 0. So it's a subspace of 0, which is a subspace of convergent sequences, which is a subspace of bounded sequences. So हमारा जो Banach limits का idea है, it concerns this L infinity. Banach limit में ऐसे लिखता हूँ, let me write down this as a theorem. Theorem states there is a linear functional f from L infinity. यानी इस L infinity पे हमेशा एक functional ऐसा है in a map that is scalar valued, linear and continuous such that which has these properties. Pehla, a norm of f is equal to 1 is equal to f of a, where of course a is this bounded sequence 1 1 1 so on. Har jagah 1, sari entry is 1. And b, if x belongs to C, if x is any convergent sequence, C का मतलब ये convergent sequences, and then f of x is just the limit of the sequence. Yani on this subspace C, it is just the limit of the sequences, where of course this x is equal to x1, x2, क्योंकि as a number exists करता है. So then actually for over this subspace, क्योंकि I'm saying this is a bounded linear functional on L infinity, लेकिन C पे इसका action simple है. यानी जो K पे जा रहा है L infinity का map F, ये जो ये subspace है C, इस पे इसका action simple है. मतलब you can find a functional on the whole space such that when restricted to the subspace, it is just the limit of the sequence. And C part, if x belongs to L infinity and such that xn इसकी जो entries है वो non-negative है for all n, then f of x is also greater than equal to 0. यानी अगर इसकी entries सारे terms जो है sequence की non-negative है तो इसका जो value है मतलब it relates the functional to the actual जो अंदर terms है ना उनकी properties के साथ एक तरह से. Then there is D. वो ये है if x belongs to L infinity and x bar is the shifted version of this sequence and x bar is x2, x3, so on and so forth. तुम्हें remember करना है x का मतलब है x तो यहाँ है ना हर जगह x is equal to x1. अगर हम इसको shift करें towards left, then the value of the functional is same. यानी f of x is equal to f of x bar, x dash x prime, not bar. It is true where of course you know that x क्या है. X is a bounded sequence x1, x2, so on and so forth belonging to infinity. तो ये चार parts हम prove करेंगे. मुझे लगता है पहले हम A and D prove करेंगे. B and C के लिए वो जरूरी है. So then we are going to, चलो मैं नीचे लिख देता हूँ. F is called the Banach limit. F is called the Banach limit. Banach limit इस वजह से because on C it is the limit of a sequence, and furthermore its existence, its limit key, depends upon Hahn-Banach theorem. So we have to use Hahn-Banach theorem to show that this exists, and since it exists as a limit of the sequence on this subspace C, so you know that's why we call it Banach limit. Okay, let's do proof. Now let y be equal to, अब मैं थोड़ा सा यहाँ से इस तरह से लूँगा, y be equal to x minus x bar, x prime, मैं bar क्यों कह रहा हूँ, where x is any bounded sequence. अब पहली बात तो ये है कि तुम्हें सोचना है x है हमारा a bounded sequence x1, x2, so on and so forth, और x prime से मेरा मतलब है इसको left की तरफ shift करेंगे, that's x2, x3, so on and so forth. Then we claim that then y is a subspace of L infinity. So by that I mean, देखो x minus x prime क्या होगा? It would be of course x1 minus x2, x2 minus x3, so on and so forth. ठीक है ना? so what? So पहले तो ये है कि it is a bounded sequence, obviously, है ना, because it's like xi minus xi plus 1, and that will be less than equal to xi plus xi plus 1. लेकिन क्योंकि ये bounded sequence है xi, so this is less than equal to c plus c, that's 2c. मतलब there would be some number जिसके मतलब it's a bounded sequence, so it is contained within L infinity, उसमें तो कोई शक नहीं. लेकिन क्या ये closed है with respect to these difference or what you call vector addition and scalar multiplication? तो वो easily check हो सकता है yes. क्यों? क्योंकि अगर मैं लूं, कैसे लूं, suppose इजी है वैसे प्रूव करना, लेकिन मैं क्या चाहता हूँ, आई वॉन्ट टू नोटेशन क्या यूज करूं, लेट y z belong to y, ठीक है ना, then y would be of the type, it would be of this type, some y1 minus y2, चलो इसी तरह से लिखते हैं, y2 minus y3 so on and so forth, where y y1 y2 so on and so forth belongs to infinity, right? इसी तरह से z भी इसी टाइप का होगा, z1 minus z2, z2 minus z3, comma so on and so forth, where z1 z2 जो ये sequence है, it belongs to infinity. Now consider y plus z, वो होगा y plus z1, right, minus y2 minus z2, ये इसका पहली term, then y2 plus z2 minus y3 minus z3, so on and so, इस type की sequence. Now clearly y1 plus z1 comma y2 plus z2, because L infinity is a vector space, belongs to L infinity. और तो मतलब ये जो differences of sequences इस type की, then this must belong to y. So y is close with respect to vector addition, and of course scalar multiplication भी ऐसे ही prove होगा. So मैं मान लेता हूँ y is a subspace. ठीक है? We show that distance of A from y closure is equal to 1, and you have to remember what is A. A is equal to 1 1 so on, मतलब जिसकी सारी entries 1 है, वो वाली sequence. और distance का मतलब तुम्हें पता ही है क्या है, यानी मैं ये बताना चाहता हूँ, देखो मैंने लास्ट टाइम ऐसे कहा था, d a y bar is nothing but infimum y belongs to y bar norm of a minus y, और मैंने कहा था a plus y भी लिख सकते हैं because y range is our, because y is a subspace, that's the only reason, otherwise नहीं. ओके, तो हम ये क्लेम करना चाहते हैं d a y bar is equal to 1. Now clearly d a y bar by definition is equal to infimum y belongs to y bar norm of a plus small y, which would be less than equal to norm of a infinity. Of course यहाँ पे norm infinity है, और इसका norm क्या है, under sup norm this is equal to 1. Now वो क्यों है, infimum is less than equal to one of the entries in the set, and a is one of the entries in the set because 0 also belongs to y bar. It's a subspace, it must contain the origin. Okay, so हमें दिखाना है बराबर है, so we show that ये 1 के बराबर है और less than 1 तो खैर है ही. Now we want to show that this is equal to 1. अगर मुझे मतलब ये तो मैंने प्रूव कर दिया less than equal to 1, और मुझे दिखाना है equal to 1 है, तो मुझे दिखाना है it cannot be strictly less than 1. Now assume to the contrary. यानी इसको कॉन्ट्रडी करने के लिए DA bar is strictly less than 1. ठीक है ना? Then there would exist x belonging to L infinity and delta positive such that norm of a minus x bar x prime sorry in infinity is equal to 1 minus delta, है ना? तो कोई ना कोई इस y bar में होगा, यानी y में होगा which is of this type such that, यानी जब y में होने का मतलब it is of the type x minus x prime where x belongs to infinity, यानी इसका norm जो होगा less than 1 होगा, है ना? क्योंकि मैं चाहता हूं अगर मैं चाहता हूं इसका इन्फिमम लेस देन 1 आए तो कम से कम एक तो होना चाहिए लेस देन 1, क्योंकि अगर सभी ग्रेटर देन इक्वल टू 1 है तो इन्फिमम लेस देन 1 कहां से आएगा? सो मैं ये मान के चलता हूं वहां एक वेक्टर होगा जिसका नॉर्म लेस देन 1 होगा, which is the same thing as saying it must be 1 minus delta for some delta positive. ठीक है? Okay. Now for n equal to 1, 2, 3, so on and so forth, I can say real part of this complex number 1 minus xn plus xn plus 1, real part of any number is less than equal to the modulus, yani 1 minus xn plus 1, that would be less than equal to the supremum of these scalars over all n, and iska jo supremum hoga wo hoga norm of a minus x, ऐसे मैं लिखता हूँ x minus x prime, which is equal to 1 minus delta. I hope it's clear, क्योंकि इसका एंट्री है 1 हर जगह और इसकी तो है xn minus xn minus 1, वही हुआ प्लस जब माइनस को अंदर लेगा. So I must have this thing. Now using the properties of real part of a sum of numbers is equal to sum of the real parts that you already know. So it implies that real part of xn plus 1 is less than equal to real part of xn, 1 cancel ho gaya, minus delta for all n running from 1, 2, 3, so on and so forth. Right? Okay. इसको अगर मैं ऐसे लिखूं, चलो मैं रफ पे थोड़ा सा करता हूँ. Now let's see. इसका मतलब हुआ real part of x2 is less than equal to real part of x1 minus delta, and real part of x3 is less than equal to real part of x2 minus delta, which is less than equal to real part of x1 minus delta, that is real part of x3 is less than equal to real part of x1 minus 2 delta, है ना? I think नहीं होना चाहिए x2, बिल्कुल सही. Now similarly real part of x4 होगा less than equal to real part of x1 minus 3 delta. So इसका मतलब ये है real part of xn plus 1 अगर मैं ये करूं should be less than equal to real part of x1 minus n times delta. Right? Right. So it implies that real part of xn plus 1 must converge to minus infinity as n approaches infinity. Lekin this is real part of a bounded sequence. So real part of a bounded sequence would be bounded. So which is a contradiction? Contradicting that x equal to x1, x2 belongs to L infinity. It cannot be bounded sequence. So hence, तो हमें मिल गया distance from A to Y bar is exactly equal to 1. नाउ बाय हान-बानाक थ्योरम, नाउ यहाँ पे हमारा मिलेगा फंक्शनल जो मैं चाह रहा था, ये बानाक लिमिट जिसको हमने की बाय हान-बानाक थ्योरम. एक्चुअली वन ऑफ द कॉन्सिक्वेंसेस जो हमने कल की थी, देयर एग्जिस्ट f belonging to L infinity star, that means a bounded linear function on L infinity, such that f is 0 on y and f of a is equal to distance of a y bar, which we have proved is equal to 1, and norm of f is equal to 1. Actually, norm of f is equal to norm of a, which we know is equal to 1 in this case. ये हमारा वो एक consequence of the Hamm-Banach theorem है. So ये हमने extend किया और ये y की हर चीज को kill करता है, right? Now since x minus x prime belongs to y, it implies that f of x minus x prime is equal to 0, and since f is linear, it implies that f of x is equal to f of x prime for all x belonging to L infinity. तो इससे हमारा बेसिकली प्रूफ हो गया, आई थिंक ए एंड डी. एक तो ये ए में ये प्रॉपर्टी थी और डी में ये है कि f of x is equal to x prime for all x belonging to L infinity. यानी शिफ्ट से कोई फर्क नहीं पड़ेगा. व्हाट इज द वैल्यू ऑफ द फंक्शनल. सो लेट्स प्रूव द अदर टू. सो या लिखते हैं यहाँ पे, दिस प्रूव्स ए एंड डी. दिस प्रूव्स ए एंड डी. ठीक है. अब बी एंड सी बचा तो बी पे आते हैं. Now let x belong be a convergent sequence. Let x belong to this small c. And then of course the limit and लिखता हूँ मैं, चूंकि इसकी लिमिट फिर एग्जिस्ट करेगी xn, let's call it L, and you have to remember that x means this thing. Okay, which implies अगर ये इसको कन्वर्ज करता है, कन्वर्जेंस का मतलब in simple analysis is for any epsilon positive, there exists a positive integer. Let me call it this n, such that modulus of xn, modulus of x sub n minus this L is less than epsilon for all n greater than equal to this capital N. Let y be equal to x comma x sub n, मतलब हमने यहां से शुरू की गिनती अब n से. ठीक है, राइट. मतलब जहां पे ये कंडीशन ट्रू है, xn minus l ने n has to start from capital N, तो मैंने अब दूसरी सीक्वेंस बनाई, मैंने उसको शिफ्ट कर दिया टुवर्ड्स लेफ्ट, बाकियों को खत्म करके जिनके लिए ये कंडीशन ट्रू नहीं है. देन फ्रॉम f of x is equal to f of x prime, जो हम प्रूव कर चुके हैं, it implies that f of x prime then must be equal to f of x double prime, क्योंकि हम इसको फिर से ऑपरेट करेंगे. where I mean x double prime है जहां मैंने दो टर्म्स को शिफ्ट किया था. ठीक है ना. and repeating the process n minus 1 times, I can do this. Process, I will get f of x is equal to f of x prime is also equal to f of x, which is equal to f of x double prime, so on and so forth, which would be equal to f of y. That is, I will get f of x is equal to f of y. क्योंकि ये शिफ्ट करते करते हम n-1 टर्म्स के बाद यहाँ पहुंच जाएंगे. n-1 टर्म जो लेफ्ट पे है वो खत्म हो जाएगी. I will get this. Now consider, यहीं पे लिख देता हूँ क्या है. Consider this y minus l, ये जो लिमिट है which is a number, into vector a. So it would be equal to xn minus l comma xn plus 1 minus l, so on and so forth. Now remember that a is just 1 1, so on and so forth. It means l times a is l l l l, और जब subtract करेंगे तो ये मिलेगा. Okay, we see that. इसके बाद norm of y minus this LA is equal to supremum of j greater than equal to n. सीधा ही जो इसकी definition है, xj minus l, which is less than epsilon because of that convergence thing, because of this thing. For all n greater than equal to n, xn minus l is less than epsilon. So applying that here, this should be less than epsilon, arbitrarily small. And since norm of f is equal to 1 is equal to f of a, जो हम प्रूव कर चुके हैं, we have f of x minus l, which is equal to, जो हम प्रूव कर चुके हैं, f of x is equal to f of y. In this case, it is equal to f of y minus l, which I can write as f of y minus la. Why? Because f of a is equal to 1 and f is linear. Now, since it's a bounded linear function by Hahn-Banach theorem, this should less than be less than equal to norm of f into y minus la, which is less than epsilon, because norm of f is equal to 1, and this is strictly less than epsilon. And since this is true for since epsilon is arbitrary, it implies that this proves b. F of x is equal to l, which is equal to limit n approaches infinity xn. For all, of course, x was an arbitrary sequence, the convergent sequence. Okay, ये ज़्यादा मुश्किल नहीं था. So that proves b. I think अब बचा हमारा c. चलो c करते हैं. To prove c, या पहले मैं यहाँ लिखता हूँ. Finally, to prove c, suppose there exists, there is some sequence, there is some x equal to x1, x2, so on and so forth, belonging to L sub infinity, right? Such that xn is greater than equal to 0 for all n. Okay? Now, if xn is equal to 0 for all n, then f of x is equal to 0, and there is nothing to prove. है ना? हमें क्या दिखाना है c में? अच्छा, मैं रिपीट करता हूँ. c में हमें दिखाना है if x is equal to some x1, x2, such that xn is greater than equal to 0, then this f of x is also greater than equal to 0. It's real and non-negative. तो पहले अगर सभी टर्म 0 हैं तो it is a 0 vector, और 0 vector तो f भेजेगा 0 पे, यानी अगर xn सारे के सारे 0 है तो f of x is equal to 0, and we have proved in a way this condition. So nothing to prove. So let xn be not equal to 0 for some n belonging to the set of natural numbers. मान लो इसकी कोई term non-zero है, then I can think of let z be equal to x by the, मतलब सुप नॉर्म फिर इसका 0 नहीं होगा, तो इसके सुप नॉर्म से मैं डिवाइड करूंगा, I will get another sequence. मैंने कहने का मतलब है मेरी सीक्वेंस जो z है वो बेसिकली है x1 divided by this number x infinity, x2 divided by x infinity, right? Then इसके जो components हैं, let's call this now z1, z2. चलो, so if z is equal to z1, z2, so on and so forth, then I know that ये जो Zn होगा ये नॉन नेगेटिव होगा क्योंकि x के सारे नॉन नेगेटिव है, बट ये लेस देन इक्वल टू 1 भी होगा क्योंकि xn, चलो मैं ऐसे लिखता हूँ, Zn इज इक्वल टू xn मॉडुलस डिवाइडेड बाय, of course this is less than equal to 1 because xn is less than equal to supremum over n greater than equal to 1 xn, which is the same thing as norm x infinity. So this is what we have. Okay, okay, and assume to the contrary, assume that f of z is negative, but then norm of a minus z in infinity would be less than equal to 1. Can you see that? Because इसका norm जो होगा, it would be supreme, मतलब मैं यहाँ लिख देता हूँ, कैसे लिखूँ? Norm of a minus z infinity would be equal to supremum n greater than equal to 1 minus zn. तो ये जो 1 minus zn है और zn जो है वो पॉजिटिव है ना, वो लेस देन इक्वल टू 1 है, तो इसका मतलब ये सारे नंबर्स लेस देन इक्वल टू 1, सो ये लेस देन इक्वल टू 1 है, राइट? एंड f of a minus z is equal to f of a minus f of z, right? Which is equal to 1 minus f of z. And remember this, what is f of z? F of z is equal to f of this thing, because I am assuming that f of x is negative, है ना? चलो ठीक है. So अब अगर f of z नेगेटिव है, अगर f of z, यानी अगर f of x नेगेटिव है तो f of z भी नेगेटिव होगा, बिकॉज f इज लिनियर और ये जो स्केलर है ये नॉन नेगेटिव है जो बाहर आ जाएगा इफ यू मल्टीप्लाई अ नेगेटिव नंबर बाय, तो अच्छा मैं ऐसे लिखता हूँ, फिर वो मैं लिखूंगा. नाउ दिस वुड बी ग्रेटर देन 1 इफ f of x is नेगेटिव, है ना? अगर f of x नेगेटिव है तो f of z नेगेटिव है, उसका मतलब 1 minus f of z, you are subtracting a negative number means you are adding a positive number, therefore this thing would be greater than 1. So यहाँ मैं लिखता हूँ, if f of x is negative then I should have f of a minus z equal to this thing which is greater than 1 and क्या, which is a contradiction, because which is a contradiction. Why? Because norm of f is equal to 1. We have proved that because norm of f is equal to 1. तो रीजन मैं यहाँ पे लिखता हूँ, norm of f 1 होने का मतलब ये है कि सुप्रीमम ओवर ऑल x infinity less than equal to 1 मॉडुलस ऑफ f of x जो है वो 1 के बराबर है, ठीक है? और अगर मैं यहाँ जाता हूँ and I have shown that norm of a minus z infinity is less than equal to 1, तो अगर ये वेक्टर जिसपे मैं f अप्लाई कर रहा हूँ वो लेस देन इक्वल टू 1 है तो उसका सुप्रीमम 1 है, तो इट शुड इम्प्लाई दैट f of, by this condition you would imply that f of a minus z is less than equal to 1. और मैं देख रहा हूँ यहाँ पे अगर f of x नेगेटिव है तो f of z नेगेटिव है, तो इसका मतलब ग्रेटर देन इक्वल टू 1 है. So this would contradict that, this is a contradiction because norm of f is equal to 1 and this proves जो बचा था C. So that was about Banach limits. अब मैं सोच रहा हूँ मैं शुरू कहाँ करूँ नेक्स्ट चीज. So let me start with introduction to this theorem, what we call Markov-Kakutani theorem. By the way, कोई क्वेश्चन इसके रिगार्डिंग? ये तुम्हारे सिलेबस में है या कि नहीं? कोई क्वेश्चन नहीं? ये सब सो रहा है।
नो सर, नो सर।
ओके, तो मार्कऑफ कापुटानी थ्योरम जो है, इट टॉक्स अबाउट, चलो मैं स्टेटमेंट पहले लिखता हूँ, थोड़ा सा माउथफुल है लेकिन उतना भी, मतलब फिक्स्ड पॉइंट थ्योरम्स आर इंपॉर्टेंट, इट्स वन ऑफ देयर दोस फिक्स्ड पॉइंट थ्योरम्स है। सो लेट मी फर्स्ट स्टेट इट, तो फिर मैं एक एक बात को क्लियर कर जाऊं। लेट S be a non-empty, अब ये ध्यान रखने वाली बात है, कॉम्पैक्ट कॉन्वेक्स subset of a normed linear space X. Then every commuting family that commutes of continuous affine maps from S to itself has a common fixed point. हमारा टाइम यहाँ से खत्म हो रहा है, मुझे लगता है मुझे फिर से रिपीट करना है। चलो अब जितना भी होगा, पहले तो ये है कि S, ये तो तुम समझते हो, व्हाट्स अ कॉम्पैक्ट सेट, राइट? कॉन्वेक्स सेट इन अ नॉर्मल लीनियर स्पेस, राइट? Because X is a normal linear space, so it is a metric space. तो metric space वाली सारी चीजें, या it's also a topological space, तो topological space वाली सारी चीजें अप्लाई होती हैं। और you know that compactness की definitions हैं, मतलब metric spaces के लिए, topological spaces के लिए वो सारी अप्लाई होती हैं। जैसे topological space के लिए जनरल जो compactness की definition है वो है every open cover can be, मैं इसको बंद करता हूँ, फिर हम नए से शुरू करेंगे क्योंकि इट्स लेस देन 1 मिनट, क्योंकि मुझे फिर से लिखना पड़ेगा, तो मैं इसको एंड करता हूँ।